Hi, welcome to part 8 of my series of presentations about the best methods for alkylating carbon nucleophiles. In this video, we'll have a look at the electrophilic alpha alkylation of nitroalkanes. These are readily available, highly versatile synthetic intermediates, but their alkylation is not always easy. Nitroalkanes are similarly acidic as 1,3-dicarbonyl compounds and can therefore be deprotonated by weak bases such as alkali carbonates or sodium hydroxide. The resulting nitronates, though, are not very nucleophilic. The addition to aldehydes or electron-deficient alkenes usually works well because O-alkylation by these electrophiles is reversible. Alkylations by alkyl halides or related electrophiles does, however, not usually proceed as expected. O-alkylation is often the preferred pathway, what causes the electrophile to be oxidized and the nitroalkane to be reduced to an oxime. With tertiary alkyl halides, surprisingly, nitroalkanes can sometimes be alkylated, but by intermediate formation of radicals by single electron transfer. Fortunately, some catalysts have been found which enable alkylations of nitroalkanes that, without catalyst, only yield an oxidized electrophile. There are three main strategies for the preparation of nitroalkanes: the alkylation of inorganic nitrite, the oxidation of oximes, amines, isocyanates, or other organic nitrogen compounds, and the direct nitration of alkanes with nitric acid. CH-acidic compounds such as beta-ketoesters or malonates can also be nitrated under basic reaction conditions with organic nitrates. Here are three examples of the alkylation of nitrite. Even hard electrophiles can give acceptable yields of nitroalkanes, but organic nitrites, the products of O-alkylation, are usually formed as well. As easier to handle synthetic equivalent of chloromethane, chloroacetic acid can be used to methylate sodium nitrite. Because only nitroacetic acid decarboxylates, pure nitromethane is obtained upon distillation of the reaction mixture, while the O-alkylated isomer remains in the still. Instead of chloroacetic acid, chloromethane can, however, also be used. Similarly, nitroethane can be prepared from sodium nitrite and diethyl sulfate. The oxidation of oximes with peracids is a convenient strategy for the preparation of secondary nitroalkanes. A much more economic strategy, suitable for the commercial production of nitroalkanes, is the direct nitration of alkanes, for instance of propane. Also methane, ethanol, or acetic acid can yield nitromethane upon direct nitration with nitric acid. Such procedures require careful optimization and are best suited for large-scale continuous production. Nitroalkanes are highly reactive and can be converted into many other useful products. Reduction of nitroalkanes gives oximes, amines, or even alkanes. The latter, in particular when using tin hydrides or silanes as reducing agents with intermediate formation of radicals. Nitroalkanes may also eliminate nitrite and be converted into alkenes. Then there are a number of procedures that convert nitroalkanes into aldehydes or ketones, for instance the NEF reaction. Nitromethane is particularly base-sensitive and dimerizes to metazoic acid or nitroacetic acid in the presence of sodium or potassium hydroxide, but other nitroalkanes do usually not dimerize in this way. Treatment of terminal nitroalkanes with dehydrating reagents such as isocyanates can bring about the formation of nitrile oxides, and in the presence of reducing agents of nitriles. Then, some methods have been developed to oxidize nitroalkanes to carboxylic acids. The main advantages of this C-C bond forming reaction is that the starting materials are readily available and inexpensive, and that the products are synthetically versatile. The main disadvantage is the low nucleophilicity of nitronates and the large number of potential side reactions. Moreover, some nitroalkanes are rather unstable, for instance those with electron withdrawing groups in alpha or beta position. This is a typical oxidation of benzyl bromide with 2-nitropropane. Despite the high concentration in mild conditions, no benzylated nitropropane was obtained. If these same reactants are treated with sodium terts butoxide and 20% of a copper catalyst in cyclohexane, no O-alkylation or oxidation, but a rather clean benzylation of nitropropane occurs. The apolar solvent cyclohexane was probably required to slow down the O-alkylation sufficiently to allow the C-alkylation to occur. In this example, 10% of a nickel complex was required to alkylate the starting nitroalkane. The fact that even a tertiary alkyl iodide could be used with success points to a radical nucleophilic substitution. This example is also similar to the previous two, but in this instance just 2.5% of catalyst was enough. The chiral enantiomerically pure nickel catalyst mediated a diastereo and enantioselective alkylation despite the use of a racemic secondary alkyl bromide as a starting electrophile. With the aid of trifluoromethylsulfonium salts, it is possible to trifluoromethylate enolizable nitroalkanes. In this case, 2 equivalents of DBU turned out to be optimal. Nitroalkanes undergo Michael additions readily, and many examples of such reactions have been reported. In this example, nitroethane could be added to a racemic substituted acrylate in high yield and with high enantioselectivity. Due to their high acidity, though, such products are configurationally labile and probably difficult to transform into more stable products without racemization. So what are potential side reactions? Nitroalkanes with electron withdrawing groups in beta position sometimes readily eliminate nitrite. In this example, an oxazole was acidifying enough to cause the complete beta elimination of nitrite by DBU. The desired nitroalkane could only be obtained in low yield when less base was used. Occasionally, the Michael addition of nitroalkanes to electron-deficient olefins gives isoxazolines as byproduct. It is assumed that these are formed by 1,3-dipolar cycloaddition of the oxygen-protonated nitronates, so-called nitronic acids, to the alkene. As already mentioned, nitronates are often alkylated at oxygen, even by soft electrophiles. Apolar solvents can help to slow down this unwanted side reaction. Primary nitroalkanes can be alkylated twice, and nitromethane even 3 times. This may be prevented by avoiding a large excess of alkylating reagent or by working with an excess of nitroalkane. Nitronates can be hydrolyzed to aldehydes or ketones by a number of different procedures. Both oxidative and reductive strategies have been reported, and nitroalkanes are in fact valuable precursors of carbonyl compounds. Nitronates are also readily oxidized by single electron abstraction, and many examples of oxidative dimerization of nitroalkanes have been reported. Nitromethane even dimerizes just upon mixing with aqueous sodium hydroxide to yield the sodium salt of metasonic acid. At higher temperature, nitroacetic acid is obtained. These dimerizations are, however, unique and not usually observed with other nitroalkanes. On this and the next slide, I've listed a selection of some more examples of nitroalkane alkylations. The alkylation by alkyl halides isn't a very common reaction because only recently suitable catalysts for a more general application have been found. Here are more examples of the alkylation by electron-deficient alkenes, aldehydes and ketones, and 2 review articles. The next video is about the Friedel-Crafts alkylation of arenes, which are the weakest nucleophiles of this series of presentations. Despite its advanced age, new improvements of this reaction are constantly being reported. I've tried to summarize the most useful procedures, so don't miss it out.